So as promised, this part 2 is all about cardiac output and blood pressure and the components that determine those. We'll then go on and look at how blood pressure is physiologically regulated by the body. And like in a lot of other systems, we have two possible routes. We have a neural control and we have a hormonal control. The neural control starts with the baroreceptors, which are mechanoreceptors, and is quite quick acting, very quick acting. It's what stops you falling over when you stand up from a chair. And then we'll look at RAS, the renin, angiotensin, aldosterone system. There's a couple of other things in there that we'll find out about as well. And this is a much slower regulator of blood pressure. So this is all really going to be about blood pressure and its regulation. Which brings us on to cardiac output. And we have two circulations. We have the pulmonic and we have the systemic circulations, of course. But all in all, unless you put a great big hole in it and have a massive hemorrhage, the circulation is a closed system. So what goes out must come back. So what goes out of the left ventricle eventually returns to the right ventricle via the systemic circulatory system. So therefore, cardiac output must equal venous return. If we're talking about blood pressure, and we'll be talking more about that in the second video, but blood pressure is determined by cardiac output and peripheral resistance. It's actually blood pressure equals cardiac output times peripheral resistance, or BP equals CO times PR. And I will be repeating all these sort of quasi-equations, if you like, throughout the videos to keep that in mind. So blood pressure is a combination, if you like, of cardiac output and peripheral resistance. Peripheral resistance, of course, we're talking about the general circulation. We're talking about the blood vessels. But because half of blood pressure, if you like, or probably more than half when you look at the factors that come into play, is about cardiac output. So in order to understand blood pressure, we need to understand cardiac output. So, okay, cardiac output is basically the amount of blood pumped out by the left ventricle in 1 minute. So there's a time component there. Because there's a time component, that time component, of course, is going to be heart rate. So cardiac output equals stroke volume times heart rate. CO equals SV times HR. Stroke volume is the volume of blood pumped out by a ventricle each beat. That's fairly logical, isn't it, when you think stroke volume times heart rate? Heart rate being the number of beats, cardiac cycles, per minute. If we look at a normal adult, try and find one, and look at the figures for that. So we're working with cardiac output equals stroke volume times heart rate, remember. So if stroke volume is 70 mils, and we'll take our average heartbeat that we talked about before in terms of timings, 75 beats per minute, we've got 70 mils times 75 beats per minute. If you can quickly work that out, well done. Otherwise, I'll tell you. That makes cardiac output 5,250 mils, or in more understandable terms, 5.25 litres per minute. Remember, cardiac output is over the course of a minute. Strangely enough, normal adult blood volume is about 5 litres on average. Average resting cardiac output in adults is 5.6 litres per minute for men, 4.9 litres per minute for females. We do have a cardiac reserve, and this is the difference between resting cardiac output and maximal cardiac output. And it can vary quite humongously, and this tends to be tucked away in the spleen for when we need it. So, okay, going back to blood pressure. Blood pressure equals cardiac output times peripheral resistance. Cardiac output equals stroke volume times heart rate. So in order to alter cardiac output and therefore blood pressure, we need to alter stroke volume or alter heart rate, or, as what usually happens, you alter both. If you increase, you will increase stroke volume, increase heart rate, you increase cardiac output, and consequently, of course, you will increase blood pressure, and vice versa. So to look at cardiac output, we need to look at both stroke volume and heart rate. In terms of stroke volume, as it is the volume of blood, as we said, pumped out by the ventricle each beat. So that's going to be somewhat dependent on how much blood we're putting in and how much blood is left in once we've contracted. The difference will obviously be stroke volume. We need to leave a little bit in the chambers, otherwise they'd stick together. It's a bit like air in the respiratory tract. You can't take it all out. So stroke volume is end diastolic volume minus end systolic volume. If you think about those terms, end diastolic volume is going to be the amount of blood just before contraction, so at the end of diastole. So we've filled the chambers, they haven't started contracting, they haven't lost any blood. That's end diastolic volume. If you take away the amount of blood left in, end systolic volume, it will give you stroke volume. So stroke volume equals EDV minus ESV. If you can't remember which way round they go, I always try and remember it as D comes before S in the alphabet. So end diastolic volume then is the volume of blood that collects in a ventricle during diastole. So the amount of blood in the ventricle just before the ventricle contracts. And systolic volume is the volume of blood remaining in the ventricle after systole, after contraction. It's the amount of blood in the ventricle just after it has contracted. If you take ESV from EDV, so EDV minus ESV, it will give you stroke volume. If you times stroke volume by heart rate, it will give you cardiac output. If you times cardiac output by peripheral resistance, it will give you blood pressure. So, okay, let's do another little calculation. So we can calculate stroke volume. And if you can remember, before we had stroke volume at 70 mils. Let's see if we can make it. So using normal adult values, end diastolic volume is 120 mils per beat or per cardiac cycle. And systolic volume is 50 mils per beat or per cardiac cycle. So we're going to take 50 away from 120, which gives us 70 mils per beat. So 120 minus 50 equals 70 mils. So there's our stroke volume gone off through the aorta. On exercise, stroke volume can increase. So if we increased stroke volume, we're going to increase, look at the calculations down below. So if we increase stroke volume, we increase cardiac output. If we increase cardiac output, we increase blood pressure. Yes? So stroke volume is end diastolic volume minus end systolic volume. So end diastolic volume, this is, remember, the amount of blood in the heart just before contraction. It's affected by something, or known as something called preload. Preload, which is a pretty vague term as far as I'm concerned, preload is about venous return. This is where it starts becoming a bit more logical. The amount of blood returning to the heart is what is going to be in those chambers before they contract. Venous return has other factors that affect it, but the biggest single factor is blood volume. It's also the only factor really that we can change, we can regulate. So venous return is primarily about blood volume. Blood volume can be altered. Blood volume is reduced by something called pressure natriuresis and by natriuretic peptides. So we're talking here about ANP and BNP. Blood volume is increased by RAS, the renin-angiotensin-aldosterone system. Okay, so this is where it all starts to get a bit abstract. Preload. Preload is the degree that cardiac myocytes are stretched just before they contract. Obviously, they fill up, they stretch a bit. The amount of stretch determines the amount of contraction at systole. Increased stretch equals increased contraction. And this was something that was stated by Otto, Frank and Ernest Starling in the Frank-Starling law. It's quite interesting that sometimes you'll see in text them use the name as Frank Starling, as in Frank being a first name. It's not. It's Otto, Frank and Ernest Starling. They did some experiments on frogs and dogs 100 years ago. It was always frogs and dogs. Anyway, the more you stretch, basically, the ventricles is what they're saying, the more they will contract. What they're really talking about is recoil. You stretch them and those elastic fibers and the contractile myocytes snap back again. They recoil. It's not really contraction in terms of active contraction, in terms of myosin heads interacting with actin, etc. And later we're going to be talking about something called contractility. Contractility relates more to proper contraction. So note that we're calling this contraction, we're not calling it contractility. It's one thing with this topic, you're going to have to keep those terms separate in your head. And I think probably the easiest way, although they called it contraction, is in your head translate that as recoil to help. So the most important factor here contributing to this stretch is the volume or speed of venous return. Venous return increases preload, i.e. stretch, and therefore increases recoil, contraction, recoil. So, okay, when thinking about this, it's quite helpful to think about a balloon. So the more air you put in, the more explosive the deflation when you let go. So you just blow a balloon up a little bit, it just thuds around the room, doesn't it, and drops to the floor. Put a lot of air in, it goes whizzing around the room. So, okay, if we increase preload, increase venous return, what would happen in terms of end diastolic volume? It would go up, wouldn't it? You increase venous return, you increase preload, you increase end diastolic volume. If you increase end diastolic volume, you will increase stroke volume, and also cardiac output. So, as we said before, blood volume is the primary factor in determining venous return. And blood volume is determined by water. Remember, most of blood is water. So the more that water we have in the bloodstream, the more blood volume we will have. And that water can come from ingestion, or it can come from reduced excretion. It's regulated primarily by the kidneys, of course. We have glomerular filtration. Factors that decrease blood volume, so blood volume is high, in order to decrease it, we have a passive process called pressure natriuresis, and we have natriuretic peptides. Both of these will increase glomerular filtration rate and cause us to excrete more water and reduce the blood volume. Things that increase blood volume is the renin-angiotensin-aldosterone system, RAS. And this is one of our key mechanisms for regulating blood pressure. It's a very slow mechanism, slow and persistent, unlike other mechanisms like the autonomic nervous system. Of course, if you alter blood volume, you're going to alter venous return, preload, and therefore end diastolic volume. You'll also alter stroke volume because stroke volume equals end diastolic volume minus end systolic volume. You'll alter cardiac output because cardiac output equals stroke volume times heart rate. And blood pressure, because blood pressure is cardiac output times peripheral resistance. So blood volume is a key factor in cardiac output and blood pressure. There are other factors that affect venous return. They have some effect, they're not regulated. And generally, if you have a fairly healthy heart, you can compensate for them. So we have things like the muscle pump mechanism from the lower legs. Of course, our muscles contract and they pump the blood back, so they are going to help with venous return. In a similar way, there's also the respiratory pump. So here we're changing thoracic pressures. So right venous return is increased on inspiration, left venous return is increased on expiration. There's also the issue of posture. So this is where you get people standing for long periods of time. You get dependent vascular pooling. So in other words, all the blood sinks to your feet and stays there. And you get orthostatic hypotension. Generally, in healthy hearts, that doesn't happen. Another problem, those of you that have had children might be aware of this one, is vena cava compression. So here we've basically got something pressing on the vena cava, which is going to obstruct the venous return from getting back to the heart. Things that do this, babies in the uterus, press, particularly when they get bigger, and also the Valsalva maneuver. And apparently this is why heavily pregnant women are told to lie on their side so baby's not pressing on the vena cava. So these are all factors that really we have no control over other than lying on your side when you're pregnant. So we've talked about end diastolic volume. The other component of stroke volume is end systolic volume. So stroke volume is end diastolic volume minus end systolic volume. Now the key thing here is there's an inverse relationship with stroke volume. If you think about it, end systolic volume, we're talking about the amount of blood left in the heart, the amount that hasn't been pushed out as stroke volume. So if you increase the end systolic volume, you're going to reduce stroke volume. If you reduce end systolic volume, more blood has been pushed out, therefore you've increased stroke volume. End systolic volume is affected by contractility. I said we'd get to contractility. Contractility is an active process. This is really about contraction. Because what we're talking about is an increase in calcium availability within the contractile cardiomyocytes. And of course, if we increase the availability of calcium, more calcium to stimulate contraction. So we increase the strength of contraction on systole, and that's what contractility is about. So if you increase contractility, you increase the strength of contraction. As I said, it's not the same as increased contraction due to stretch and preload. So try and think of that in preload as recoil rather than contraction. And this is what I was saying about this inverse relationship. If contractility increases, so if you think about this, the strength of contraction increases, there's going to be less blood left in the ventricle. So if there's less blood, we're talking about ESV being reduced. So if contractility increases, ESV reduces. If ESV reduces, stroke volume will increase because we've got less left in. Less left in the chamber means more is moved out, and that's stroke volume. So if ESV reduces, stroke volume increases. And of course, if we increase stroke volume, we increase cardiac output, we increase blood pressure. Afterload, we're just going to mention afterload. Afterload isn't regulated, not without the help of a surgeon anyway. What we're talking about here is the back pressure. We're talking about resistance in either the pulmonic or the systemic circulation against which the myocardium has to push against on systole. So if we have a high afterload, if we have a lot of resistance, we're going to need to increase contractility to push those valves open against the back pressure and eject blood into either the pulmonic or the systemic circulation. It's increased by things like sticky valves. So if you have an aortic valve stenosis, of course it's stiff, it's sticky, it won't open, a bit like a stiff door. You have to push harder to open it. So that's afterload. There's a lot of resistance there. The other thing is systemic hypertension. Because of course, if you've got a high blood pressure, the heart is going to have to work harder to push against that. That hypertension is acting as afterload. So in this case, if you increase the resistance, what's going to happen to ESV? ESV will increase because you've had to try and push against all of this. In healthy hearts, a little bit is not going to be a problem because you can increase contractility to compensate. But in some cases you can't in an unhealthy heart, in heart failure. So you can't push against it. So you will end up with an increase in end systolic volume. If you have an increase in end systolic volume, of course, you're going to have a reduction in stroke volume. So let's have a quick recap on blood pressure then. So we said before, blood pressure is cardiac output times peripheral resistance. Cardiac output is stroke volume times heart rate. Stroke volume is end diastolic volume, the amount of blood in the ventricles just before contraction, minus end systolic volume, so the amount of blood that's left in the chambers after contraction. End diastolic volume relates to preload. Remember Frank Starling and the stretch and recoil. It relates to venous return because obviously the amount that preloads the ventricles is what is coming back. And most of venous return is about blood volume, and that is the thing that we can regulate. End systolic volume, the amount of blood left in the chambers after contraction, is reduced by increased contractility. And if we think about it, if you reduce it, that will increase stroke volume because more blood has left on that contraction because you increased the contractility of the myocardium. ESV is increased by afterload. Remember that's the back pressure that it has to push against. So we're talking about things like aortic stenosis and systemic hypertension. But these are things that we can't easily regulate. But the impact they're going to have is that if you have increased afterload, you're going to need to increase contractility in order to push against that afterload and open those semilunar valves. So to alter blood pressure then, we can alter the cardiac output, we can alter peripheral resistance. They are the two components of blood pressure. Or we can alter both, which is usually what happens. To alter cardiac output, we can alter stroke volume, or we can alter heart rate, or both. And again, this is usually what happens, you alter both. To alter stroke volume, we can alter the end diastolic volume, and we're going to do this by altering the blood volume, or we can alter the end systolic volume, and we do this by altering contractility, or we can do both. So let's talk about end diastolic volume. We've said the major component of this is blood volume. And this is the thing that we can regulate, either up or down. The thing that decreases blood volume and pressure is pressure natriuresis. Pressure natriuresis, it's a simple process that almost happens, if you like, by accident, but not by accident. It's quite helpful. It's a passive process providing constant regulation. And it's all about altering glomerular filtration rate. Hence, you've got a picture there of a glomerulus and a Bowman's capsule. When blood volume and pressure is increased, and you can imagine it going into that glomerulus, it's going to increase glomerular filtration rate because you've got an increased hydrostatic pressure within that glomerulus, within those capillaries, that's going to push more fluid out into the Bowman's capsule to go off down the loop of Henle and through the convoluting tubules. So more blood in via the afferent arteriole, the arteriole coming into the glomerulus, causes an increase in hydrostatic pressure. This increases water filtration via glomerular filtration. So in other words, it increases the glomerular filtration rate, which then, as long as you don't reabsorb it in the tubules, will increase excretion and, of course, reduce blood volume because you're losing fluid from the blood. So the volume of water in the blood reduces, consequently, blood volume reduces. If blood volume reduces, then venous return is going to reduce and end diastolic volume is going to reduce. So reduced blood volume reduces preload, end diastolic volume, stroke volume, cardiac output, and therefore blood pressure. So this is a passive process of increasing glomerular filtration. A slightly more active process that decreases blood volume and therefore decreases blood pressure are chemicals called natriuretic peptides that I bet you've heard of because we're talking about atrial natriuretic peptide, ANP, and this is secreted by the arterial myocytes. We're also talking about BNP, not the British Nationalist Party, brain natriuretic peptide. And this is secreted by ventricular myocytes in humans. It's called brain natriuretic peptide because, of course, it was probably first discovered in pigs, and in pigs it comes from the brain. It's stimulated, its secretion is stimulated by stretch receptors. We'll talk about these later. This is part of the Bainbridge reflex. So when blood pressure is high, it activates stretch receptors in the atria, and this stimulates the secretion of ANP and BNP. Also, it's stimulated by the sympathetic nervous system, by endothelin-1, which is a vasoconstrictor secreted by endothelial cells. And in that case, the idea is that we need to maintain glomerular filtration rate if blood pressure is low. Because you can imagine, it's the opposite of our pressure natriuresis. If blood pressure drops, glomerular filtration is going to drop. So we need to maintain it because although, yes, we want that water back to increase blood volume, we want to get rid of the waste, the solutes that we want rid of, things like urea. We don't want to retain that. So we need to maintain glomerular filtration. But in that case, what happens is the water is then reabsorbed through various mechanisms we'll talk about later. So the blood volume is not actually reduced. But generally, the function of our natriuretic peptides is to decrease blood volume. So it increases glomerular filtration rate, but this time in a slightly more active way than pressure natriuresis does. It dilates the afferent vessel going into the glomerulus, and it constricts the efferent arteriole going into the glomerulus. And you can imagine you're increasing the lumen size of the vessel going in, you're reducing the lumen size of the vessel going out, so consequently you're going to increase hydrostatic pressure within that glomerulus. You're going to sort of engorge the glomerulus in blood, if you like, which is going to push more water out. So you're increasing glomerular filtration. It also, around the loop of Henle sits in the medulla of the kidney. Lots of medullas, I know. But the loop sits in the medulla, the Bowman's capsule sits in the cortex, and otherwise the outside of the kidney. In the medulla, what happens is that the natriuretic peptides increase the blood flow around the loop of Henle. Now, a lot of water is reabsorbed from the loop of Henle, and that reabsorption is dependent on an osmotic gradient with the tissues of the medulla of the kidney. If you increase the blood flow in those tissues around the loop of Henle in the medulla of the kidney, it reduces the osmolarity because you're removing more solutes. Because of that, you reduce the fluid reabsorption from the loop of Henle. So you're discouraging, if you like, the water from being reabsorbed from the loop because you've reduced the number of solutes in the tissues around the loop. It's also, natriuretic peptides are also a powerful vasodilator. So if you've got increased blood volume, of course, vasodilation is going to decrease that blood volume. We'll talk about that more when we talk about peripheral resistance. And it inhibits RAS. It inhibits RAS because, of course, RAS has the opposite effect. So let's have a look at our natriuretic peptides then. So here's our glomerulus again. This time we've got added on a loop of Henle, very carefully drawn using a mouse. That's quite tricky. And we've got our glomerulus sitting there. And you notice that the afferent arteriole, the efferent arteriole are more or less the same lumen size, same diameter. They must be. I copied and pasted the second one, so it must be the same size as the first one. Okay. So what happens when we get AMP and BMP secreted is that it dilates the afferent. And you can see now our afferent is much, much bigger than the efferent because we also constrict the efferent. We're going to get increased glomerular filtration, and we're going to have a loss of blood volume because we've moved more water out into the tubules. Probably increase our urine output as well. The other effect, if you remember, was this increase in the blood flow around the loop of Henle, which is going to give us a reduced osmotic gradient and reduce the water reabsorption from the loop. Therefore, the water will stay in the loop, it will get into the convoluted tubules, and finally it will get into the collecting duct, the bladder, and will increase excretion, but will also reduce blood volume. So we increase water excretion via glomerular filtration, and we reduce the water reabsorption back into the blood. This is going to reduce blood volume. If we reduce blood volume, we reduce preload, end-diastolic volume, stroke volume, cardiac output, and therefore blood pressure. So that's our pressure natriuresis, our natriuretic peptides. They all help to decrease blood volume and therefore decrease blood pressure. The one that increases it when blood pressure is low is RAS, the renin-angiotensin-aldosterone system, aka RAS. It increases blood volume and therefore, of course, increases blood pressure. So to activate it, we have these little mechanosensitive juxtaglomerular cells around the afferent arteriole. These are often called intrarenal baroreceptors. We'll talk about other baroreceptors later. And these are found around the afferent arteriole. So you can imagine this is a very good place to monitor what's happening in terms of the pressure of the blood coming in. When blood pressure is low, these juxtaglomerular cells, because they're mechanosensitive, will detect this. When they detect it, they secrete a hormone called renin into the blood plasma, hence the R in RAS. Renin goes off and it converts angiotensinogen that's produced by the liver into angiotensin 1. Angiotensin converting enzyme, sound familiar, ACE, that's produced from the pulmonary and renal endothelial cells, then cleaves that angiotensin 1, which is inactive, into the active form, angiotensin 2. We now have the active sort of product, if you like, of this system, angiotensin 2. Angiotensin 2 does a few things, but it also needs to recruit some mates to help it. So, as we said, what happens is, to get angiotensin 2, we get low blood pressure detected by those juxtaglomerular cells around the afferent arterioles of the glomeruluses. Glomeruluses or glomeruli? Oh well. Once they're activated, they secrete renin into the circulation. Renin secretion is also stimulated by a few other things. One is the sympathetic nervous system, which is quite interesting because, as you'll see in a minute, angiotensin 2 stimulates the sympathetic nervous system. They're obviously good buddies. Another thing that stimulates it is a reduction in sodium, and this is detected by little macular denser cells around the loop of Henle. But in our case, we're talking about blood pressure, so we've got low blood pressure, which is stimulating the secretion of renin. Renin then converts angiotensinogen, which is produced by the liver, into angiotensin 1. Angiotensin converting enzyme, ACE, from, remember, pulmonary and renal endothelium, then converts angiotensin 1 by cleaving it into the active form, angiotensin 2. So, all fairly straightforward. So, as I said, angiotensin 2, although it has its own actions, and we'll talk about those in a minute, also recruits some mates. It's got a couple of chemical mates and a neural mate. So it recruits other mediators, and the function of all of them, of course, is to increase cardiac output and therefore increase blood pressure. Remember, RAS cuts in when blood pressure is low. So the first mate it recruits is aldosterone, aldosterone being the second A in RAS. Aldosterone is secreted from the adrenal cortex because, of course, it's a steroid hormone. In the distal tubule, aldosterone increases sodium, water, and water reabsorption, mainly through stimulating sodium reabsorption. It does this by increasing the activity of the sodium-potassium ATPase pump and also sodium channel activity. And it does this, of course, being a steroid hormone, by direct gene activation. Remember that? Direct gene activation. Our steroid hormone goes straight into the cell and binds to a receptor. So, as we said, this increases sodium reabsorption. And of course, where sodium goes, water follows. So it increases water reabsorption, thus reducing blood volume. Another old friend, it stimulates the secretion of antidiuretic hormone, ADH. ADH, of course, is secreted by the posterior pituitary, but synthesized in the, hypothalamus. ADH binds to its own receptors, known as V2 receptors, on the epithelial cells in the collecting ducts of the kidney. So after we've gone through the nephron, these all empty into collecting ducts in the medulla of the kidney. When it does this, it increases the expression of aquaporins. Aquaporins, if you remember, are water channels. And what it does is it puts an aquaporin on the renal side of this epithelial cell, on the tubular side, and one in the other side of the cell, on the side that empties out into the medulla of the kidney, so that the water can pass through the epithelial cell and then be reabsorbed into the blood. When it's reabsorbed into the blood, of course, it's going to increase blood volume. So it increases the expression of aquaporins and therefore increases water reabsorption. And our neural mate. So angiotensin II enhances the effects, the activity of the sympathetic nervous system. The sympathetic nervous system increases heart rate, increases contractility. So there we're affecting both components of our cardiac output, and it also causes vasoconstriction. So here we're impacting on peripheral resistance. So through those three effects, and we'll go over those three effects again when we talk about the autonomic nervous system, those three effects, if they're activated by the sympathetic nervous system, will increase blood pressure. So there we have two sets of tubular effects, so effects within the kidneys, but also we've got the systemic effect of the sympathetic nervous system. So angiotensin II has its own actions as well. Angiotensin II can be abbreviated to Ang2. So generally, most of the time, it binds to its own receptors that are A21 receptors. So angiotensin II binds to these receptors for various effects. It vasoconstricts. So not only are we talking about the sympathetic nervous system vasoconstricting, so noradrenaline from the sympathetic nervous system has its receptors. In this case, we've got angiotensin II binding to 81 receptors on vascular smooth muscle to enhance that vasoconstriction. If you vasoconstrict, you increase peripheral resistance. And therefore, of course, blood pressure, because blood pressure equals cardiac output times peripheral resistance. Angiotensin II also stimulates the thirst centers in the brain. If you stimulate the thirst centers, you get thirsty, you drink more fluid. So here it's not about reabsorbing fluid that we would have excreted. It's about putting additional fluid into the system. So it increases the blood volume. And it has its own effects in the kidneys, primarily around sodium and water reabsorption, of course. And this happens at several different sites within the nephron. So angiotensin II binds to its receptors in multiple nephron segments, and what it does, it directly affects various ion transporters to increase sodium and therefore water reabsorption. It also has an effect, remember when we were talking about naturally uretic peptides having the opposite effect in the medulla of the kidney. Angiotensin II, though, decreases blood flow to the medulla of the kidney around that loop of Henle. If you decrease the blood flow, you decrease the clearance of solutes, things like sodium, chlorine, urea. They don't get cleared from that medullary space around the loop of Henle. This increases the osmolarity around the loop of Henle, and of course it increases water reabsorption. So in this case, we're reabsorbing the water because in this case we want to increase blood volume, unlike our natriuretic peptides that wanted to decrease blood volume. So if we have a look at a nice little nephron, not drawn by me, but it is free license, and look at the renal effects of RAS. And here you can see the top where we've got the glomerulus and the convoluted tubules. They're all in the renal cortex. The loop of Henle then hangs down into the medulla. And the collecting duct, of course, has to pass through the medulla to get to the pelvis of the kidney and then on down to the bladder. So angiotensin II, starting in the medulla. This is the last thing we talked about. Angiotensin II increases osmolarity in the medulla by reducing the clearance of solutes so that more water is reabsorbed from the loop of Henle. Angiotensin II also increases sodium and water reabsorption in multiple segments of the convoluted tubules, both the proximal and the distal convoluted tubules. Aldosterone, if you remember, increases sodium and water reabsorption in the distal tubule by playing around with that sodium-potassium pump and various sodium channels to increase the sodium reabsorption from the tubules back into the systemic circulation, and of course water will follow, so that will increase water reabsorption. And we have our ADH. Remember, ADH increases the expressions of aquaporins in the collecting duct, causing increased water reabsorption. So having talked about RAS, RAS is a slow regulator of blood pressure. Remember, I've said this to you before, I think. Where you have a chemical or hormonal system, it's generally much slower acting, but perhaps more persistent than the neural equivalent. And we've got the same thing here. RAS and our natriuretic peptides, they're all quite slow acting. However, the autonomic nervous system provides rapid and constant regulation of blood pressure, even to the point of making the necessary changes to allow you to stand up suddenly without getting all dizzy and falling over. So it's much, much quicker. First of all, let's have a talk about blood pressure generally. So, definition of arterial blood pressure is the pressure exerted by the blood against the walls of the arteries. Fairly straightforward, I would have thought. We can split it down though, and you may have heard some of these terms, and some of you probably know these terms and what they mean. We have systolic pressure. Systolic pressure, as it implies really, is the maximal pressure on systole. So we're talking about in the arteries here. Diastolic pressure is the lowest pressure, so it's at diastole. And if you look at our diagram here, you can see we've got systolic pressure, diastolic pressure there, and a bit in the middle. And this is arterial. And down the bottom, we're talking about exactly where that is. Yes? So that's all arterial. When we're talking about venous pressure, of course, we're much, much lower. So pulse pressure, again, you can see on the diagram, that's this width here we've got of the whole sort of band, that zigzaggy red band. We can calculate it by taking the systolic pressure and then take away the diastolic pressure. Mean arterial pressure, you can see there's a line in the middle. So that's mean always means average, of course, so we know how to calculate averages. Mean arterial pressure is systolic pressure plus diastolic pressure and then divide by 2. So in exactly the same way as you do to get an average. So that gives us some definitions. And remember, to alter blood pressure, we talked about this, you can alter cardiac output and alter peripheral resistance because BP equals CO times PR. To alter cardiac output, we can alter stroke volume or alter heart rate or both because cardiac output equals SV, stroke volume, times HR, heart rate. To alter stroke volume, we can alter end diastolic volume, and if you remember, we did that by altering blood volume. We can also alter end systolic volume by altering contractility. So stroke volume is EDV, end diastolic volume, minus end systolic volume. So let's look at some of those factors. So we've already talked about blood volume. So we've talked about altering end diastolic volume, and this is decreased by pressure natriuresis or by natriuretic peptides, but it's increased by RAS. The ones we're going to talk about, we're going to talk about the sympathetic nervous system and the parasympathetic nervous system now, because we're talking about the autonomic nervous system, and those are the two branches. In terms of end systolic volume, the sympathetic nervous system increases contractility, therefore reducing end systolic volume, but increasing stroke volume. The parasympathetic nervous system reduces contractility. So of course that's going to increase end systolic volume, which is going to reduce stroke volume. So to alter cardiac output, the autonomic effects are the sympathetic nervous system increases heart rate, the parasympathetic nervous system reduces heart rate. And peripheral resistance are other component of blood pressure alongside cardiac output. So the sympathetic nervous system vasoconstricts, which increases peripheral resistance. And if you remember, also angiotensin II vasoconstricts. The parasympathetic nervous system, though, has no systemic effect on vessels. It does affect some vessels, mainly vessels supplying glands and in various other areas. The meningeal vessels, for example, can be vasodilated by the parasympathetic nervous system. But generally, vessels are not. There is no parasympathetic effect on them. So what we can see here is, of course, that the sympathetic nervous system increases blood pressure and the parasympathetic nervous system reduces blood pressure. The autonomic nervous system is sort of home, really. It's a bit like hormones have their home in the hypothalamus. For the autonomic nervous system, we're talking about the medulla oblongata. In relation to cardiovascular, we have cardiac centers and we have a vasomotor center within the medulla. In terms of the sympathetic nervous system, our nerve, both afferent and efferent, is the cardiac sympathetic nerve. It innervates the SA and the AV nodes plus the myocardium. And if you remember, our sympathetic nervous system have a chain of ganglia, the sympathetic chain, either side of the spine. Up until that point, the sympathetic nervous system uses the neurotransmitter ACH. But post-ganglionic, the neurotransmitter that we're talking about that binds to all these receptors and has all these effects is noradrenaline. But those receptors, almost all of those receptors, will also bind adrenaline. Adrenaline, of course, comes from the adrenal medulla. It's one of our catecholamines that was secreted from the adrenal medulla. And that adrenaline can bind to many of the same receptors as noradrenaline. The parasympathetic nervous system, our nerve, afferent and efferent, is the vagus nerve, which is cranial nerve 10, of course. The preganglionic and postganglionic neurotransmitter is acetylcholine, ACH. So if we have a receptor that binds acetylcholine, we know it's parasympathetic. If we have a receptor that binds noradrenaline, we know that it's the sympathetic nervous system's receptor. So this isn't a case of turn on one and turn off the other. The sympathetic and the parasympathetic work together to maintain a balance, if you like, maintain homeostasis within individual cells. So even in a single cell, you will have effects from the sympathetic nervous system balanced by effects from the parasympathetic nervous system. And between them, they can regulate up or down by one of them perhaps becoming a little more dominant than the other. So in all relevant cells, there is a balance of sympathetic and parasympathetic influence. In that band in the middle where they overlap, we're talking about normal functioning values, i.e. homeostasis. But one can dominate over the other. If you enhance one, it will start to dominate and that will then make finite adjustments that will affect blood pressure. It's a bit like a seesaw of sympathetic versus parasympathetic, and it can change second by second. So we're talking about very rapid adjustments here inside individual cells. Okay, so let's talk about contractility. We talked about it a little bit in the first part, but here we're going to talk about it in terms of regulation, really. Contractility, the other term for it is inotropy. Anything to do with heart rate is chronotropy, chronos as in time. Contractility is inotropy. So you might see inotropic changes, inotropic drugs. That's what it's referring to. So remember, contractility is nothing to do with preload. It's nothing to do with that stretch which causes increased contraction, i.e. recoil. So it's a much more active process. It's regulated by the autonomic nervous system. The sympathetic nervous system increases contractility. In other words, it increases the strength with which the myocardium contracts on systole. This is going to reduce end systolic volume because we're pushing more out, and increase stroke volume because that's where it's gone, into stroke volume. The parasympathetic nervous system, of course, does the opposite, reduces contractility, so we have less of a push on systole, which is going to leave more blood in the chambers afterwards. So it increases end systolic volume, and because it's left in the chambers afterwards, it hasn't gone out with stroke volume, so it's going to decrease stroke volume. So here's our end diastolic volume. So this, remember, is just before contraction. We've filled up the chambers. Contraction happens, and we push out stroke volume, leaving end systolic volume in the chamber. So increased contractility is going to increase, of course, stroke volume, is going to increase cardiac output, increase blood pressure, etc. It also helps to maintain stroke volume if the heart rate increases. And when you bear in mind the sympathetic nervous system does both, we need increased contractility to compensate, because what we're doing is we're effectively reducing the time by increasing heart rate allowed for the filling of the chambers. So remember, when we have diastolic filling, that's what we're doing, is we're gathering up all that, what will be end diastolic volume. So end diastolic volume will be reduced if the time is shorter for those chambers to fill. So to compensate for that, you need to increase contractility to make sure you push more out and reduce end systolic volume. Okay, so let's have a look at see how we can regulate contractility. So here's our contractile cardiomyocyte. If you remember, they have nice sarcomeres in them and all the usual equipment of contraction. So to increase contractility, the sympathetic nervous system exocytoses its neurotransmitter, usual neurotransmitter, noradrenaline. Noradrenaline on contractile cardiomyocytes binds to beta-1 adrenoreceptors. You've heard of beta-1s, I'm sure, on those contractile cardiomyocytes in this case. when it does that, these beta-1 adrenoreceptors in this circumstance are coupled to a stimulatory G protein. Remember our little G protein? I've missed out there the whole G protein and the beta and gamma and all the rest of it, because hopefully you know that now. So all we've got here is an activated alpha subunit. That activated alpha subunit, that's stimulatory, binds to adenylate cyclase, and because it's stimulatory, it activates adenylate cyclase. So what does adenylate cyclase do? Yes, adenylate cyclase converts ATP into cyclic AMP. Cyclic AMP then activates protein kinase A. Remember, protein kinases, their main role is to phosphorylate things. They're all about phosphorylation. So protein kinase A phosphorylates calcium channels in the plasma membrane, in the sarcolemma, and in the sarcoplasmic reticulum. Of course, these, if you remember, when we talked about excitation in contractile cardiomyocytes, we had calcium influxing through these, in addition to through the gap junctions, but also because it was influxing through the channel in the membrane, that calcium was then stimulating even more calcium release from the sarcoplasmic reticulum. So we had calcium-induced calcium release. So here, what we're doing is we're affecting 3 of the different ways that calcium comes in. We're not affecting the gap junctions, but the other ones, the major ones. So our protein kinase A, once activated with cyclic AMP, phosphorylates calcium channels in the plasma membrane and the sarcoplasmic reticulum. They become sensitized by this phosphorylation, which means that they open more readily. If they open more readily, it increases the amount of calcium influx from outside our contractile cardiomyocyte and also released from the sarcoplasmic reticulum. If we have increased calcium availability, it will increase the contraction within that contractile cardiomyocyte. So it will increase contractility, the strength of contraction. But this is where we get our seesaw effect. To decrease contractility, the parasympathetic nervous system exocytoses its neurotransmitter, acetylcholine, which then binds to M2 cholinergic receptors. And you'll notice the name. We've got an adrenoreceptor for noradrenaline or adrenaline. Adrenaline binds to that one too. And we've got a cholinergic receptor for acetylcholine. So the clue is in the name. These are M2, also known as muscarinic cholinergic receptors, possibly on the same cardiomyocyte. When ACH binds, in this case the M2 cholinergic receptor is coupled to an inhibitory G protein. So what happens is that G protein becomes activated, but the alpha subunit is inhibitory. So when it binds to adenylate cyclase, it blocks it. So it's blocking adenylate cyclase, so our GS can no longer stimulate it. And if you remember, cells have lots of adenylate cyclases throughout the cell. So it depends how many of these are getting blocked or activated is going to give us that seesaw effect in terms of cyclic AMP availability. A GI will reduce it, a GS will increase it. So noradrenaline, sympathetic nervous system, will increase cyclic AMP. Acetylcholine from our parasympathetic nervous system will decrease cyclic AMP. Because we've decreased cyclic AMP, our calcium channels are less likely to open. So the calcium availability will be reduced. If calcium availability is reduced, of course, contractility will be weaker. So not only will contractility have to be increased to cope with increased heart rate, it also needs to cope if afterload increases. So it needs to be increased in that case because afterload is the resistance against which you're pushing. So if you've got a lot of resistance, you need to push harder. In other words, contractility needs to increase. Afterload is this load, the resistance, that the heart has to eject blood against. And of course, this is going to affect both the systemic circulation, so it's going to relate to aortic pressure from the left ventricle and pulmonic pressure from the right ventricle. Common causes, we talked about the ones affecting the left ventricle before. This is systemic hypertension, because of course we've got a pressure of blood in the vessels that we need to push against that pressure. And also more mechanical things like aortic stenosis, because we've got a stiff, sticky valve, a bit like a very stiff door. You have to push harder against it to open it. Pulmonary hypertension will increase right ventricular afterload. This might be caused by things like COPD or pulmonary emptiness. Increased afterload increases end systolic volume, of course, because of course you're trying to push out against some resistance, so you're going to get less blood out, so there will be more left in the chambers. It's going to decrease stroke volume. So if afterload is increased, contractility has to be increased to reduce end systolic volume and increase stroke volume. And this is where, of course, we start to get into the realms of heart failure, because if you have a constant afterload that you have to push against, so you have to keep a constantly high level of contractility, eventually the myocardium starts to fail. So in healthy hearts, they're less adversely affected because you do have the ability to increase contractility for short periods. The myocardium is able to respond to the sympathetic nervous system and increase contractility. In heart failure, it can't. Okay, so that contractility was inotropy. This was altering the inotropic situation, if you like. Heart rate, if you remember, I said it is chronotropy, chronos as in time. And heart rate is also regulated by the autonomic nervous system. Again, we have the cardiac centers in the medulla oblongata, not the medulla in the kidney. They contain the cardioacceleratory center, guess what that does, and a cardioinhibitory center. So I think we know which one's which. The sympathetic nervous system, as we said, increases heart rate. The cardiac sympathetic nerve, remember, is our nerve of choice here, innervates the SA and the AV nodes from the cardioacceleratory center in the medulla. The parasympathetic nervous system decreases heart rate. It does it via the vagus nerve, which innervates the SA and the AV nodes, but this time from the cardioinhibitory center. The PNS actually gives a constant vagal tone because if you remember, the inherent rate of the SA node is 100 beats per minute. We don't want to operate at 100 beats per minute for any particular length of time because, again, we're into the realms of heart failure. So this vagal tone keeps the SA node down below its inherent rate most of the time until we need to increase heart rate. And remember, cardiac output is affected by heart rate because cardiac output equals stroke volume times heart rate. So we've talked about stroke volume. Now we need to talk about how we can regulate heart rate. So here's another infamous diagram. This time we're in an autorhythmic cardiomyocyte, one of those pacemaker cells. Okay, so here's our noradrenaline, exocytosed from our cardiac sympathetic neurons to receptors on autorhythmic cardiomyocytes in the SA and the AV nodes. It binds again to beta-1 adrenoreceptors. It activates again a stimulatory G protein which binds to adenylate cyclase. And of course, because it's stimulatory, adenylate cyclase then takes ATP and converts it into cyclic AMP. This time, instead of activating protein kinase A, cyclic AMP in this context actually sensitizes the funny sodium channel and the transient calcium channel. If you remember, these are the channels that open at -60 and -50 to create the pre-potential, that slope before in the autorhythmic pacemaker potential, before we get to threshold and depolarization, that little slope there. So cyclic AMP sensitizes these channels. When we've talked about channel sensitization, this makes them open more readily. So the funny sodium channels and the transient calcium channels open more quickly. Because of this, this shortens the pre-potential. It makes that slope steeper. However, of course, we've got to have our seesaw. So in this case, again, we've got muscarinic M2 cholinergic receptors. To those, ACH binds from the parasympathetic vagus neuron, and it then activates another G protein, but this time that G protein is inhibitory. We have an alpha subunit, binds to adenylate cyclase, but it inhibits it. It blocks the adenylate cyclase from producing cyclic AMP. So again, we've got this balance of cyclic AMP availability within this single cell. Because of that, of course, our funny channels and our calcium channels won't be sensitized. If they're not sensitized, that pre-potential will take longer to reach depolarization. The slope of it will be longer rather than steeper. So changing the steepness of that pre-potential, there's our little pre-potential down here, changing the slope of that, the steepness of that, will change the frequency of depolarizations. If you change the frequency of depolarizations, of course, each depolarization is a heartbeat, so you will change heart rate. So the sympathetic nervous system makes that steeper. We've got greater sodium and calcium influx during that pre-potential, gives us a steeper slope. Threshold is reached more quickly, increasing the frequency of the heart rate. And you can see there the distance between our peaks of depolarization are quite short. So we've got far more beats for our money, if you like. The parasympathetic, however, the parasympathetic inhibits the sodium and the calcium influx during the pre-potential. We've got a less steep, longer slope. Threshold is reached more slowly, so that drives those depolarizations further apart. So in this case, we've got a much bigger gap between heartbeats because we've got a bigger gap between the depolarizations. So it reduces the frequency of the heart rate. So what's going to cause this other than our autonomic nervous system? So positive chronotropic factors, in other words, things that increase heart rate, are, as I'm sure you know from before your exams and various things, probably going into work at the moment, stress, anxiety, and excitement. And this is due to sympathetic stimulation. Primarily, it's going to be adrenaline released because of the limbic system activating its release. The Bainbridge reflex we'll talk about, and again, this is sympathetic stimulation to increase heart rate. The baroreceptor reflex uses sympathetic activation to increase heart rate. Thyroxine, we know that if you're hyperthyroid, you have an increased heart rate. Hypothermia, when you're hot, your heart rate also goes up. And electrolyte imbalances, like hypokalemia. Negative chronotropic factors, things that drive the heart rate down. We know about vagal tone. Vagal tone we have most of the time because we don't want our heart to beat at 100 beats per minute generally. So the vagal tone is about parasympathetic driving the SA node inherent rate down. The baroreceptor reflex uses the parasympathetic nervous system to drive heart rate down. Also, heart rate goes down generally with age. So your maximal heart rate apparently equals 220 beats per minute minus age in years. I'll leave you to work that one out. Hypothermia, we know heart rate goes down in hypothermia. And of course, the opposite electrolyte imbalance, in this case, we have hyperkalemia. Which brings us on to peripheral resistance. So we've talked a lot about cardiac output, but we also need to talk a little bit about peripheral resistance. And as we've suggested before, it's mainly about vasoconstriction versus vasodilation. But regulation is less about parasympathetic, it's more about the sympathetic branch vasoconstricting at different levels. So most vessels are not innervated by parasympathetic neurons, so the parasympathetic nervous system has little effect on vessels generally, just in specific areas. And this comes from the vasomotor center. So before we were talking about the cardiac centers, the vasomotor center is also in the medulla oblongata. Again, in this case, whereas in terms of heart rate, we had a constant parasympathetic influence to drive it down or to keep it below the inherent rate, here we've got a constant sympathetic effect. We have a constant vasomotor tone provided by the sympathetic nervous system, and this helps to maintain blood pressure, because you imagine if you took away all vasomotor tone completely, okay, you'd have nice saggy baggy blood vessels, but your BP would just drop to your boots. So there is this constant vasomotor tone, and of course if we increase the effect of the sympathetic nervous system, that vasomotor tone is going to increase and we're going to vasoconstrict. So just to remind you, blood pressure is cardiac output, which we've talked about, times peripheral resistance. So to increase blood pressure, the sympathetic nervous system increases the vasomotor tone via vasoconstriction. And this can be stimulated by various things in terms of the sympathetic nervous system. Of course, angiotensin II, we have this sort of very helpful situation where it stimulates the sympathetic nervous system and the sympathetic nervous system stimulates it. But angiotensin II also binds via its AT1 receptors to smooth muscle, vascular smooth muscle cells, and causes them to contract, causing vasoconstriction, as does noradrenaline. The baroreceptor reflex uses the sympathetic nervous system, if blood pressure is low, to stimulate vasoconstriction. Stress and excitement and all the rest of it again causes vasoconstriction by activating the sympathetic nervous system. Also, if you have a high PCO2 or a low CO2, which obviously is not good, we don't want to be hypoxic, and we don't want to be hypercapnic. So if we have those, then we have vasoconstriction stimulated by the sympathetic nervous system. Of course, we did immunology, didn't we? If you have already. And we talked about local mediators and moderators of vasomotor tone in terms of that. We talked about nitric oxide as a vasodilator, for example, but it tends to work locally. So we're not talking about generally impacting on systemic blood pressure with those. So here's another diagram for you. In this case, we've got a vascular smooth muscle cell. If you remember, those are those nice little sort of tapered cells, all joined together in sheets with gap junctions between them, wrapped around the vessels, the blood vessels, in the tunica media. On their surface, they have receptors for noradrenaline. But in this case, it's not a beta-1 adrenoreceptor, it's an alpha-1 adrenoreceptor. It binds noradrenaline and also adrenaline. So along comes our noradrenaline, or adrenaline, binds to the alpha-1 adrenoreceptor on vascular smooth muscle cells. Now bear in mind, we want to stimulate vasoconstriction, so we want this vascular smooth muscle cell to contract. So what end product do you think we want?
Yeah, this is all aiming to get more calcium, isn't it? It's just the mechanism in between that we need to go over. So, okay, noradrenaline comes along, binds to an alpha-1 adrenoreceptor, vascular smooth muscle cells. This is a G protein coupled receptor again, of course it is. The G protein stimulatory is activated, and our alpha subunit then goes off and binds and activates phospholipase PIP2 complex. If you remember, this is the thing, it's an enzyme sits in the plasma membrane, uses phospholipids to make two things. Think about what one of those things is and why we might want it. Yeah. Phospholipase PIP2 produces IP3. IP3 binds to its receptor on the sarcoplasmic reticulum, where of course we store a lot of calcium. IP3 binding opens calcium channels in the sarcoplasmic reticulum, releases the calcium for contraction of the smooth muscle cell. So remember, smooth muscle cells don't have sarcomeres. We have that funky arrangement of myofilaments on the outside, secured to the outside by dense bodies. We don't need to know about how calcium activates them. You'll be glad to know. But what we do need to know, of course, is that this calcium stimulates contraction. That contraction, of course, if you contract all the vascular smooth muscle cells around a vessel, will cause vasoconstriction. Interestingly, adrenaline binds to beta-2 receptors in the arterioles supplying the myocardium. When it binds to beta-2 receptors, it causes vasodilation. And if we think of where those vessels are supplying the myocardium, yes, there we want to increase perfusion to the myocardium, because the chances are we've got the sympathetic nervous system activated, so our heart rate needs to go up. We need to increase contractility. Therefore, the cardiomyocytes need more blood, so we need to increase perfusion to the myocardium rather than vasoconstricting it. Okay, so other factors that affect peripheral resistance, our prime one really is about vasoconstriction. Blood viscosity does affect peripheral resistance, but we can't really regulate it. So viscosity refers to the resistance of blood to flow due to the component parts of it, due to its viscosity, its thickness, its stickiness. So, of course, viscosity, if you increase viscosity, you're going to increase friction against the vessel walls. And actually, often what happens in that circumstance is that the vascular endothelial cells will release nitric oxide to vasodilate that area where the friction is to try and compensate. Viscosity, of course, is going to impact on venous return because it's harder to get the blood back to the heart. It's also going to affect the effort the heart needs to put into pumping that blood around. And, of course, it's going to impact on perfusion of the tissues, so how much oxygen is being delivered to the tissues and the organs. The components of viscosity, we're talking primarily really about hematocrit, the packed cell volume of erythrocytes. We have an awful lot of erythrocytes, but if they increase or if they're deformed, then they create an increase in viscosity. Other components of the plasma, we have plasma proteins. So things like fibrinogen, immunoglobulins. So we have our antibodies flying around in the plasma, lipoproteins, of course, as well. These are all components flying around in the plasma that are going to make the blood thicker. And there's various other formed elements. So we might have other lipids, triglycerides, for example, carbohydrates, leukocytes, our white cells, and platelets. Viscosity is also affected by temperature. So in the cold, the blood is sluggish. Okay, so as I said, peripheral resistance and blood viscosity is not something that we can regulate. Things we can regulate, to recap on this, to alter blood pressure, we can alter cardiac output and/or alter peripheral resistance. To alter cardiac output, we can alter stroke volume and/or alter heart rate. To alter stroke volume, we can alter end diastolic volume by altering the blood volume and/or alter end systolic volume by altering contractility. So the sympathetic nervous system increases contractility, the parasympathetic nervous system reduces contractility. End diastolic volume is decreased by pressure natriuresis, natriuretic peptides, that AMP and BMP, but is increased by RAS. The sympathetic nervous system increases heart rate and the parasympathetic nervous system reduces heart rate to alter cardiac output. And in terms of peripheral resistance, the sympathetic nervous system vasoconstricts to increase peripheral resistance. Remember we said the parasympathetic nervous system has no real systemic effect on vessels. And as I said before, these chemical regulators, RAS and the natriuretic peptides, are slow regulators of blood pressure. They alter blood volume and end diastolic volume only. And they take a little while to kick in. The ANS, on the other hand, the autonomic nervous system, is fast and constant regulator. It affects peripheral resistance, it affects heart rate, and end systolic volume via contractility. But how do we regulate the autonomic nervous system? We know it comes from the medulla oblongata, from those cardiac centers, the vasomotor center. But what monitors blood pressure in order to tell it to do what it needs to do? So activating the autonomic nervous system, we have two reflexes. The first of these, really the lesser one, is the Bainbridge reflex. It's all about arterial stretch. It was discovered, I told you this was all about frogs and dogs, oh, and pigs, but this one was discovered in dogs by Francis Bainbridge, hence the name, in 1915, so over 100 years ago. But we've since found out that although it works quite well in dogs, the response is weaker in humans. And what this is about is stretch receptors. So these are mechanoreceptors, a bit like the juxtaglomerular cells. So they're mechanoreceptors located in both atria, and they're put in a very convenient place at the junctions of the inferior and superior vena cava and also at the junctions of the pulmonary veins. they're mechanically stimulated if the venous return, the pressure in the vena cava and the pulmonary veins, and consequently the atria, increases. So they're activated by stretch due to increased venous return. Receptors then use the vagal afferent to signal to the cardioacceleratory center. Okay, cardioaccelerating, yeah, heart rate's going to go up. So the sympathetic nervous system increases heart rate, increases contractility. And why it's doing this really to try and push the blood through quicker. We've got increased venous return. We need to get rid of the pressure in the heart, the blood collecting in the heart, and move it back through to the systemic circulation. Remember, cardiac output has to match venous return. So heart rate and contractility increase to try and decrease that venous and atrial pressure by moving the blood through quicker. Thus, of course, it increases cardiac output, but that's fine because it's matching venous return. So that's the Bainbridge reflex, activating the autonomic nervous system. Our biggie is the baroreceptor reflex. The baroreceptor reflex provides constant, rapid regulation of blood pressure. This is the sort of regulation that I said before stops you getting dizzy and falling over when you stand up quickly. It's that rapid. Again, we have mechanoreceptors like the stretch receptors. And you could, if you remember, we had the juxtaglomerular cells talked of as intrarenal baroreceptors. So we heard the term before. These are the big baroreceptors, not in the kidneys. And what they do is they detect changes in arterial blood pressure. And they do that in two really key locations. The arch of the aorta, where of course you've got blood coming out of the heart directly into the systemic circulation. And another important place is the carotid sinuses, because here it's measuring the pressure of the blood going up the carotids to the brain. What they do is they send action potentials. So the aortic baroreceptors send action potentials to the cardiac center in the medulla via the vagal afferent nerve. So that doesn't make it parasympathetic. It's that we're talking here about an afferent, not an efferent. The carotid sinuses send their action potentials to the cardiac center via the glossopharyngeal afferent nerve. So we've got another cranial nerve, in this case 9. So, as we implied, the stretching, because these are like stretch receptors and these are mechanoreceptors, the stretching of the arterial walls stimulates the baroreceptors. When they're stimulated, it opens mechanically gated, because these are mechanoreceptors, mechanically gated calcium channels. So not sodium, in this case we're opening calcium channels, but of course it has the same effect because it's cation. It will cause an EPSP effectively. That will potentially create an action potential along the vagus nerve from the aorta, aortic arch, or the glossopharyngeal nerve from the carotid sinuses to the cardiac center in the medulla. The greater the stretch, the more frequently the baroreceptors fire action potentials. And this is the key. This is how this can be monitored. So the cardiovascular center uses the frequency of action potentials that it receives from the baroreceptors to measure arterial blood pressure. So in other words, if pressure increases, there's more pressure in the aorta or the carotids, there will be more frequent action potentials. When the pressure reduces, there will be less frequent action potentials. So this enables this constant monitoring by monitoring the frequency of the action potentials. Because those baroreceptors are very close to the heart, this is going to be an extremely rapid response. And as I said, this is basically what stops your blood pressure dropping too much when you stand up. It is that quick. In response, of course, the cardiac center is then going to deploy the autonomic nervous system to regulate blood pressure. So in response to the baroreceptors, in high blood pressure where there's frequent action potentials, the parasympathetic nervous system dominates over the sympathetic nervous system. Remember, we said about this seesaw, it's not so much one on, one off. We've got this balance between the two. In this case, in high blood pressure, the parasympathetic is going to dominate. So, heart rate goes down due to that. Remember that longer pre-potential. We don't have sensitization of the funny sodium channels and the transient calcium channels. So we've got a longer slope, longer pre-potential. So that drives those depolarizations further apart and decreases heart rate. Reduced contractility. Remember, our parasympathetic nervous system blocks adenylate cyclase, so we have less calcium available in the contractile myocytes. The vasodilation that we get is going to be less about the parasympathetic, of course. This is going to be about the reduction in the sympathetic nervous system. So the sympathetic neurons secrete exocytose, less noradrenaline. So there's less noradrenaline to bind to the alpha-1 adrenoreceptors on the vascular smooth muscle cells. So less calcium available for contraction of those. So we get vasodilation. So all of this reduces cardiac output because stroke volume via increased ESV and heart rate are reduced, plus peripheral resistance is reduced. Reduction in both cardiac output and peripheral resistance, of course, is going to lower BP. Okay, so the opposite. In low blood pressure, so we've got fewer action potentials getting to that cardiac center. The sympathetic in this case dominates over the parasympathetic. So we're going to have a higher heart rate, a shorter pre-potential, bringing those depolarizations together and therefore making the heartbeat more frequent. Increased contractility, so there will be more calcium available in the contractile cardiomyocytes. Vasoconstriction, because we'll have more noradrenaline exocytose to bind to those alpha-1 adrenoreceptors on the vascular smooth muscle cells, so they'll have more calcium available, they will contract more and reduce the lumen of the vessels in vasoconstriction. This, of course, is going to increase cardiac output because stroke volume is increased because we've reduced end systolic volume, and heart rate is increased, plus peripheral resistance is increased. Of course, an increase in both is going to raise blood pressure. So, okay, to sum up, let's try and put that all together in some sort of flow diagram. So, blood pressure is about cardiac output and peripheral resistance. So, cardiac output times peripheral resistance. Peripheral resistance is increased by sympathetic vasoconstriction. Cardiac output is about two things. It's about stroke volume and heart rate. So stroke volume times heart rate. Heart rate is increased by the sympathetic nervous system, reduced by the parasympathetic nervous system. Stroke volume we can split into two components or two factors as well. Stroke volume is end diastolic volume minus end systolic volume. End systolic volume is determined by contractility primarily. I know we have afterload as well, but we can't regulate that. It's regulated by contractility. Contractility is increased by the sympathetic nervous system and reduced by the parasympathetic nervous system. And of course, if you increase contractility, don't forget you will reduce end systolic volume, but increase stroke volume. You have that inverse relationship. End diastolic volume, if you remember, what we're talking about is preload, the amount of blood that comes back into the heart, fills the chambers, causing them to stretch and recoil. And that's all about venous return, the blood coming back into the heart. The major component of that, yes, there are a few other factors, but the major component and the thing that we can regulate is blood volume. Blood volume is reduced by pressure natriuresis and by those natriuretic peptides AMP and BMP, but it's increased by RAS. Of course, what controls all of this by monitoring blood pressure and then activating it through the cardiac centers in the medulla is, in terms of neural, the baroreceptor reflex. So the baroreceptor reflex has an influence on heart rate, on contractility, and on vasoconstriction. Our other regulator, our slower regulator, that has multiple effects, is RAS. Of course, its primary role is about those changes in the renal tubules that will increase blood volume, increase reabsorption from the tubules into the blood, increasing blood volume, increasing end diastolic volume. But if you remember, as part of RAS, we have other things activated. RAS, or angiotensin II, recruits some mates. So RAS recruits the sympathetic nervous system, or enhances it, but also angiotensin II can directly cause vasoconstriction. So RAS has an impact on peripheral resistance. As we said, RAS enhances the sympathetic nervous system, so it's going to have an impact on contractility via the sympathetic nervous system. And finally, because of that enhancement of the sympathetic nervous system, RAS is also going to have an effect on heart rate and increase it. Hopefully the diagram will give you an overview. Obviously there's additional detail beforehand, but hopefully that pieces it all together for you.
So that was the end of cardiovascular. Before moving on to your final topic, respiratory, though, please make sure that you have completely understood this topic. You've started to get to a position where you can recall most of the information through doing your own notes, own diagrams, and primarily by speaking it either quietly in your head to yourself. Ask yourself questions and answer them in your head, or by having a study buddy. So please make sure, as always, that you have got this topic under your belt before moving on to the next one.